Okay. It's a very nice circle here. I hate deleting that. Okay. Let me calibrate the screen. All right. We'll be moving on to chapter 11, section 1. Okay. So now we're talking about multivariable functions. Put this up here. Okay. Multivariable functions. Okay. So for instance, we're going to have like an f of x, y, or g of x, y, for instance. Let's say we have some f of x, y is equal to 1 over 4x squared plus 1 over 2y squared. Okay. Let's consider what is the domain of such a function. What is the range of such a function? It's a two-variable function. It's a function of x and y. So let's consider what its domain is. The domain is the set of numbers that we can plug into the function that won't make the function output some type of undefined quantity. Okay. So I see some x's and I see an x here and a y here in the denominator. Clearly, I can't put 0 down there. Okay, so I can't divide by 0, but everything else seems fine, right? So the only time we'd be in trouble is if I plug in like a f of 0 of 0. Notice then I'd get 4 times 0 squared plus 1 over 2 times 0 squared. Again, I get 1 over 0 plus 1 over 0, undefined. So the only time we have something messing up is when x is equal to 0 or y is equal to 0. Okay, so we can say this in multiple different ways. We can say that this is the points from negative infinity to 0, union 0 to positive infinity for the x. Cross, again, same thing for the y. Here's your y. Another way to say it, so this is our domain. Another way to say the domain is, this is like an interval notation. We can also do it in set builder notation. We can say that the domain is a set of all x, y, an element R2, such that x is never 0 and y is never 0. So there's multiple ways of saying this same thing. Okay. Let's do another example. Oh, wait, we've not talked about the range yet. Okay, so that was domain. What is the range? So the range, we've got the domain covered. The range is the set of outputs given the allowed inputs. So the allowed inputs are anything but 0. So what are the allowed outputs? Well, you can kind of think of this as like the idea of a limit. So the limit as, you know, x, y approaches, let's say, infinity. What does f of x, y equal? Notice that if x or y get arbitrarily large, these fractions get arbitrarily small. So the output of f of xy approaches 0. What about, oh, also, notice that I could have replaced that infinity with that plus or minus infinity. Because you square a negative number, the result is the same. So I could have put plus or minus infinity over there. Next, let's discuss what about when it approaches 0. Clearly, it cannot equal 0 but it sure as heck can approach 0. So what happens when our f of xi approaches 0? Okay, that is the question. So then we have to kind of think about what would be the outputs here if the denominators get arbitrarily small. So clearly it would be divergent. The values would grow without bound. And clearly this is true whether you approach 0 from the left or 0 from the right for either x or y. So the range here will be 0 to infinity. Right? Where we don't really include 0 because we can't really plug in an infinite value. And we don't really include infinity because we really can't plug in 0. All right? So that's the domain and range of this function. Let's analyze a different function. I'll say I do miss having you guys sitting in class right now. This is boring recording a lecture. I kind of wish I could ask you guys whether you have any questions before I move on. But I had to take my aunt to the airport this morning and I could not make it to class. Okay. Let's look at another function here. What about g of xy is equal to the square root of 9 minus x squared minus y squared? What is the domain? What is the range? Okay. So we realize that if we're taking a square root, that the values inside the radical cannot dip below 0, or else we'll be getting imaginary numbers involved. So we'll set up this inequality where it can at most equal 0, but nothing less than that. Then we show that we get this when we add an x squared and a y squared to both sides. Okay, notice that when equality holds, we get this, which this implies this is a circle of radius 3 centered at the origin. Okay, and the fact that it says x squared plus y squared is less than or equal to, it's less than or equal to 9, means that what you get is for your domain you get kind of like a disk, an allowed disk right here, where this disk is x squared plus y squared is equal to 9 on the boundary, and any points inside this disk, if we input them into our function, it's allowed. And any points outside this disk, if we input them into our function, it is not allowed. Points outside this disk would output a complex number. Points inside this disk would output a real number, and that's what we want to keep it real. Okay. So we found the domain. One way to say this in set theoretic notation is that the domain is the set of all x, y, an element of R2 such that, x squared plus y squared stays less than or equal to 9. Okay. All right. So, what is the range? Well, if we know that the set of all inputs cannot allow this to equal a negative number, well, we know what the range is technically. It's all of the outputs that won't mess this up. All the inputs that won't mess this up are known. It's any x y pair such that when you add them together, they equal less than 9. So an example is 0, 0, that adds up to 0, which is less than 9. And then like 1, 1, that when you square that, 1 squared plus 1 squared is 2. So that's less than 9. 3 and 3, that won't work, you know, because you get 9 plus 9, which is greater than 9, you know. 2 and 2, you would get 4 plus 4, which is 8, you know, that's 9. Okay, great. So now we get what's going on. What is the range? So the smallest this can be is clearly 0, right? If the output, if x squared minus y squared end up exactly equaling 9, then we take the square root of 0, and then that's 0. So the smallest it can be is 0. Clearly, it can never be less than 0, and it will include that point. So we'll include 0 with brackets. So what is the largest value it can assume? Well, clearly, the largest value in the range is when these negative numbers don't overpower this 9. So minus x squared minus y squared can't exceed 9. So they have a limit. Minus x squared minus y squared, if you will, here, or it's the same thing as saying that y must be greater than or equal to x squared plus y squared. Notice that that means the limit, the highest value that these can be, is if they are indeed 0, okay? And we just take the square root of 9, which is 3. And that's included. Any non-zero values for x and y would produce something less than square root of 9, which is 3. And furthermore, if we actually plug in values for x and y that exceed square root of 9, then we're actually picking numbers that are not in the allowed domain. So we can't do that anyways. So our range must be 0 to 3. So that's the way you kind of think about it. Okay. So then let's talk about graphing these functions. We can do so by saying our g of xy is equal to some z. Okay. Then we can say, what if I square both sides of this equation? Right? And then I get x squared plus y squared plus z squared is equal to 9 when I solve, when I send the x and y over to the other side. And, you know, this is 3 squared. So notice that we get a sphere centered at the origin of a radius 3 if we do this. But notice our original quantity was this. There's just a positive sign right here. There's no negative. Notice if I were to work backwards from here and I take the square root of both sides, I don't get what's above here. I get distinctly see, the difference is you get plus or minus here, but over here you only have plus. So in order to honor what g of xy really is, we can't make it a full sphere, right? This would be the full sphere, top hemisphere, bottom hemisphere, but we can't do that because what we're given is only the top part of the sphere, okay? The top part of the sphere. So it really kind of just looks like a spherical dome. So a spherical dome, the top part of the sphere, not the bottom part, okay? And clearly it has radius 3, and it's centered at the origin, okay? So that's why that is happening. Next, we want to talk about level curves. A level curve is what happens when we plug in a constant value in for g of xy or f of xy. Basically, we set the function equal to a constant. And we draw out what that curve gives us. Okay, so let me formally define a level curve. A level curve of a multivariable function f of x, y is the curve we get when we set f of x, y equal to some constant k. K is a fixed element of the real numbers. Okay? And so we will get various level curves. So your book creates a picture. I won't be able to draw it very well, but I'll say that, you know, reference figure 4 in 11.1. The shape kind of looks like this. It's like some weird bell-looking shape, and its projections onto the XY plane make concentric circles. And so all of these concentric circles are level curves of this shape, okay? Also, let's say you had some like paraboloid shape, right? Then cross sections an elliptic paraboloid. If you look at it horizontally, the level curves would make ellipses. But if you look at it vertically, the level curves would make different parabolas. That's why it's called an elliptic parabola. It's almost like a hybrid between an ellipse and a parabola. Okay? So let's actually create some level curves and graph the level curves. Okay. Oh, and before we do that, let me just give you an example of a contour. A contour is a graph of level curves. Let's say you have this following contour map. Okay, let's say we have the following contour map. Here's my x, here's my y. What is f of 1, 3 going to equal? Well, we just look at our contour map. We move 1 on the x, 1, 2, 3 on the y. That point is this point right here, all right? It doesn't intercept any contour exactly, but it's in between this contour line of 75 and this contour line of 100. What would it mean for a point to lie anywhere on one of these contour lines? Well, that means f of this xy must equal 100. That would mean f of this xy must equal, what is that, 75. Okay, so if your contour line is not filled in enough and you have some point right here, like where we have 1, 3, we have to estimate it, right? How close is it to this contour of 75? And how close is it to this contour of 100? It's a little closer to the 75 than it is to 100. So, you know, 75 and 100 have 25 apart. So I would say over here, it's probably like 10 away from it. So I would estimate it to 85. Your estimate might be 86.5 or something like that, or maybe 84.2. Really, we're just like trying to see how to understand what a contour map looks like. So what about f of like 2, 2? We go to 2 on the x, we go to 2 on the y. 1, 2, okay, let's see where this is at. All right, it's right here. It lies in between that like 50 and something else. So it must be something less than 50, very close to 50, maybe like 47. All right. Then we'll look at another contour. What is like f of 1, 6 look like? What does that equal? Well, actually, we should probably not pick 6 Maybe we should pick 3 and maybe we should pick, because that's not there, maybe like 3 and 3. So I'll put a 3 here, a third line here. So 3, 3 would be right. Oh, would you look at that? 3, 3 would be right here. And you guessed it, that will be just our 75. If it lies right on that contour. So hopefully that, I feel like I'm beating a dead horse, but hopefully that really hits the message home. Now, let's graph some level curves. Let's give you a multivariable function, and let's graph some level curves of that multivariable function. Let's say we have some f of xy equaling 6 minus 3x minus 2y. All right. Let's calculate level curves for k is equal to negative 6, 0, 6, maybe 12. Probably not going to do all of them. Let's do some of them. So to find a level curve, let's say for k equals 6, then we set our function equal to 6. And now we just solve for what we get. So if I subtract the 6 from both sides, I get this is equal to. Then when I add this over, divide by negative 2, I get y of x is equal to negative 2 third, no, negative, I flipped it, negative 3 over 2x, right? Oh, this is an equation of a line with y-intercept going through the origin with a slope of negative 3/2. So this is our level curve for k is equal to 6. All right. What is our level curve for k is equal to 0? Let's find out. We set our function f of xy equal to 0. And just solve. So I'll bring this 2y over here. All right. Divide by 2. So I get y of x is equal to 6 minus 3x. Everything divided by 2. Notice that this decomposes 2. So I get y is equal to negative 2/3 x plus 3. Very much similar to the earlier level curve, but now it has a y-intercept 3. So I go 1, 2, 3. Here's its y-intercept. So this is going to be our level curve x for k is equal to 0. What is our level curve for k is equal to, let's say, positive 6? We just set the function equal to positive 6 and solve for y. Okay, so I subtract a 6 from both sides. Did we do positive 6? Let's do negative 6. So we did this one, let's do negative 6. So I subtract 1, I get negative 12 here. Add this, I get negative 12 plus 3x is equal to negative 2y. I'm going to get y is equal to negative 12 plus 3x all over negative 2. Then I distribute that, so I get positive 6 minus 3 over 2x is equal to my y. Very similar to earlier, but now has a y-intercept 6. So you get the picture. This is going to be k equals to negative 6. You get the picture. We can just keep doing this, and we're getting these level curves of this function, f of xy, is equal to this thing. But this thing is not a bunch of lines, is it? No. We are looking at cross-sections of this shape at constant values. So the shape really isn't these lines. This is really giving us what the shape would look like if we fixed its value, okay? Kind of like the cross sections of what we were showing earlier of the elliptic hyperboloid, all right? So why not sketch some level curves of the function we were talking about earlier, since we know that that function creates a hemisphere. we would assume that level curves of a hemisphere would project onto the XY axis in the form of concentric circles of varying radius, in which the largest radius would be the radius of the hemisphere, and in which the smallest radius would be 0, so like a dot. So our function was g of xy is equal to the square root of 9 minus x squared minus y squared. So let's find some level curves for this guy. We can let it equal any number, let k equal 0, 1, 2, 3, if you will, all right? So for k equals 0, I get 0 is equal to the square root of 9 minus x squared minus y squared. Okay, so I square both sides, I add these negative terms over, I get, boom. Our level curve here, when k is equal to 0, is the largest part of the circle. This is k equals 0. It's radius 3. It's a circle centered at the origin of radius 3, okay? But we can do it for more k's. What about k equals 1? So I get 1 is equal to the square root of 9 minus x squared minus y squared. Square both sides. I get 1 is equal to 9 minus x squared minus y squared. Add them over, subtract this. I get x squared plus y squared is equal to 9 minus a 1, which is an 8. Okay? So notice that if 8 is equal to some r squared, that implies r is equal to the square root of 8, which that means I get 2 root 2. So I'll get a circle, and this time its radius will be 2 root 2. This is for k equals 1. What about k equals 2? For k equals 2, we just set the function equal to 2. All right, square both sides, I get this. Add these over, subtract the 4, I get this. 4, 5, 6, 7, 8, 9. This becomes a 5. So I get r squared is equal to 5, which implies this is a circle of radius root 5. So then we create another concentric circle, and this is a circle of radius root 5, and this is our level curve for k equals 2. You get the picture. These are just cross sections of our hemisphere. Our hemisphere, that if this is the x, this is the y, this would be the z coming out. The hemisphere would look like this. But we're saying at constant values, project that curve onto the xy plane, and these are the values that we're getting, concentric circles. Okay. Let's do another example. How about h of xy is equal to 4x squared plus y squared plus a 1. Let's find a general level curve for this guy. Okay. So we want to make this look like a standard shape. Okay. And the way we can make this kind of look like a standard shape is to get it in a standard form of the generalized equations that we've had before. So although it may not make intuitive sense as to why, we'll be doing this step. Later on, you'll see in retrospect why we do that. Why don't we factor out a k minus 1? Okay. Notice that when I factor out a k minus 1, if I were to send the k minus 1 back, you would restore our original equation. Okay, so you'll see why we're doing this in a second. Then I can divide both sides by that k minus 1. So I'll get k all over k minus 1 is equal to this guy, all of this. And your book represents 4 in the numerator as a 1/4 in the denominator. This is k. That's just to get it in the standard form. That's a minus 1. Okay. All right. So then we notice what happens if I subtract that. What happens when I subtract that constant term over to this side? I get k over k minus 1 minus 1 over k minus 1 is equal to x squared all over 1/4 times the quantity k minus 1 plus y squared all over k minus 1. And, you know, notice that these guys have the same denominator, so we can just say that this is k minus 1 over k minus 1, and you can divide by itself is equal to 1. That is why we did this whole k minus 1 business, is because we wanted this equation to equal 1. This x squared over 1/4 times k minus 1 plus this y squared over this k minus 1. We want it to equal 1 because now we can make it look like something that's in the standard form with our standard form equations in the previous section, okay? You will notice that this looks like a special kind of three-dimensional shape. In general, for a elliptic paraboloid, you get the shape to look like this. Okay. That is our elliptic paraboloid. So notice that this equation actually does look like an elliptic paraboloid. And I know what you're wondering, why is there a z here? I don't see any z's here. Well, remember that we're talking about level curves. And this h of xy, we can actually call it z. And if z is equal to k, well, then in this standard form equation, this z could be a constant, and it could be divided by another constant, and it could end up equaling overall a constant, equaling some x squared over a squared plus some y squared over b squared. So this is actually, in fact, our z over c. It's just disguised. And this is, in fact, our a squared and our b squared. It's just disguised, okay? So let me clear up some room here. When we graph this guy, we get it to look like this. Oh no. It looks like a elliptic paraboloid because when we project down into the xy, you get a bunch of different level curves that look like ellipses. But if you project it onto, let's say, zy, you would get various parabolas. Okay, because look, this way it looks like a parabola. But look at it in a different perspective, they look like ellipses. Okay. So let's do another example of, like, let's say, finding domain and range. What about a triple value function? We're in Calc 3, so now we're starting to enter higher and higher dimensions. But because we're mathematicians, we're not scared of that because we know how to deal with things in general, okay? So this f of x, y, z, given this function, is actually a four-dimensional shape. So it's a four-dimensional mathematical entity, something that us human beings would have a very hard time trying to wrap our brains around what it looks like. But us mathematicians are very, 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 very stubborn, and we don't want to give up. So we think, well, I can't imagine what the function looks like, but maybe I can set the function equal to a constant and see what that looks like. Just like how a two-dimensional surface in R3 had one-dimensional quantities, the level curves, so this was 2 dimensions, so this was in 3 dimensions, having a 2-dimensional projection, a 3-dimension and 2-dimensional projections. This will be a 4-dimensional object, and it will have a projection or a level surface in 3 dimensions. So let's calculate the level surfaces. Before they were level curves, now they'll be level surfaces. Okay, so first, before we do anything, we need to really compute what the domain of this thing is. For instance, domain. And how do we do that? Well, we know sine can eat anything and spit anything out in terms of real numbers, but this ln function is very fastidious in its habit. So we need to make sure that this ln is not evaluating anything that is equal or less than 0. So it has to be greater than 0. So notice that this implies that z must be greater than y. So the domain is the set of all x, y, z, an element in R3 such that z is greater than y. That's it. X can just be anything. X is free. X can be anything. So that's the domain there. Now, the last thing we need to do is calculate maybe or think about a level surface of this guy. Oh, well, actually, doing a level surface for this would be very complicated. I'm sure Maple could do it for you. Doing a level surface for this guy would look very complicated. So why don't we do something that maybe I can achieve in this last little bit of the lecture. What about this function? This function, f of x, y, z, is equal to x squared plus y squared plus z squared, is actually a 4-dimensional hypersphere. Okay? Yeah, that's all there is to it. It's very difficult to visualize what a 4-dimensional hypersphere is or what it looks like. But notice that if we set this f of x, y, z equal to a constant k, then we can then calculate a level surface. Okay? Notice that this is the level surface where it produces a sphere centered at the origin of radius square root of k. And when we modulate k, when we change the values of k, it just forms spheres of greater and greater radii or lesser and lesser radii. And so the level surfaces are nested spheres spheres of various radii, okay? And when, k is equal to 0, you get a sphere of radius 0, which would just be a dot. It'd be a dot centered at your three-dimensional coordinate system at the origin. Okay? I will upload, I would say, is there any questions, but you guys aren't here. But you can email me questions. I will upload your homework problems right away for this section. See you guys in class on Friday.